you had to be a good Bayesian and change your predictions after.
So I'm curious, like, if you can tell us a bit more about how you leverage these methods in your work at Teamworks or for Toulouse, and how you, like, and maybe to come back, to what you started doing in your career, how do they help account for uncertainty and thinking about the generative graph of the model with, in particular, spatial temporal data?
Yeah, I think the word generative there that you said is really useful. That's kind of how I think about modeling problems, right? I very much think about like, what is the generative model here, and how do we, in sort of, this may be a bit oversimplistic, but I sort of think about generative model as the way of specifying the model, and Bayes is kind of the way of giving the data, how you sort of work backwards, right?
Yeah.
Sort of the Bayesian, this sort of way of thinking, right, where you're sort of pooling information across, maybe across players or across matches or across seasons or across space, or this is all like incredibly important in sports, where you have what might look like a lot of data, but there's so much sort of contextual variation combined with a tremendous amount of players. So our database in soccer is about 80,000 players, and if you sort of, just think about like, I want to fit even like an adjusted plus minus model, which is essentially like a giant regression model. It's a really, large P, small n type of problem. But of course, there's a tremendous amount of structure there, right? You have a lot of insights based on the league they play on, the positions they play on, how good, the team is, all as well as sort of individual event information that happens in the game. So you get like all this sort of super useful information and that comes from the structure of the game, and you want to be able to use that to get sort of better information, right? So when you talk about Bayesian models, that's sort of where it comes into play. Now, I should say that oftentimes what we end up doing in the end is sort of finding this balance between, hey, I want to, in my head, maybe I've specified this perfect model for this problem, but then either it's like it's too slow to fit because of the size of this data, is especially tracking data, can be absolutely massive.
Yeah.
So it's like, how do we get sort of poor man's Bayes, or like so oftentimes it's like, how can we get 90% of the value of this model for 5% of the computational cost, or 10% of the computational cost, right? So we had, there's a lot of those types of conversations go on. And then the other things that will happen is, again, is you'll sort of fit this model, and then you might, back to sort of the earlier conversation, you look at these edge cases and sort of the perimeters of the covariate space, and you're like, there's some bizarre behavior, and the model just doesn't look right in for various reasons in areas that we ultimately care about. And so then you sort of like have to think about, okay, how do we solve this, right? Do you like upweight that area of the covariate space in terms of the likelihood? Do you do sort of ad hoc corrections? Do you redefine the model, right? Like there's like all these sort of interesting things that are, I'll give you an example, one fairly recently, which is that we're building, you can imagine you have some model that says, okay, I'm gonna build component models for different skills, and then I'm gonna sort of have those skills try and predict like player performance or team performance or something. So you can actually think of this as like multiple likelihoods in the same model, right? A likelihood for, there's some latent skills, think of them as like speed and ball control and whatever, right? And then you might be observing like actual speed data and maybe some of the team performance and a bunch of things, right? So all these different likelihoods sort of stack on top of those latent variables. And it turns out that because of this, whether it's like model misspecification or collinearity or something, you can end up in these situations where okay, the speed data in theory should define everything you need to know about speed, but because of the sort of incompleteness of the data or who knows what, you end up sort of, the likelihood for team performance, what can actually happen is to say, actually the speed data says this player's slow, but because he's so good, this latent variable for speed, we're actually going to think he's really fast. And so you end up in like situations saying, no, I don't want the player's performance or team performance to sort of flow into the speed latent variable, because subjectively I think all the information should be captured from this other thing. And so you sort of end up doing things which are kind of un-Bayesian, actually, which are like cut models, where you're saying, hey, I won't, like even within, say, like a GIF sampler, right, where you're saying, I'm not going to allow this information to affect this variable, or this parameter to sort of flow into this other parameter, right? So you're, based on the underlying model, you can sort of hack these models to do very, very interesting things. Actually, this is an old idea. If you remember, WinBugs used to have this like cut option, which sort of was largely for computational reasons, but allowed you to sort of like, in some sense, cut sort of portions of the graphical model to sort of produce what you want. There's actually some really interesting papers, I'll see if I can find it later, by Pierre Jacob that looks at these models, these cut models, and they're sort of like un-Bayesian in a way, but sort of shows how they behave and how they're super useful in certain cases.
Yeah, that is very interesting. It's like, yeah, I'm not sure it's un-Bayesian. Like, to me, it's just, specifying prior information and making sure it goes through the sampler. The issue you have usually, and that's actually an active area of research, is if the model gets complex enough, it gets hard to set the priors on something you really care about. Like setting the priors on the standard deviation terms of a multivariate normal is like, you have to do it, but sometimes it's not interpretable. What you have an idea about is the standard deviation of the whole data, right? So your whole generative graph, more or less the prior you want to have on the standard deviation, but you don't know how to specify that for each of the parameters. And so ideally you would want to specify one big standard deviation, and that one is just, allocated then upstream to the rest of the model.
But this is even more weird, though, because this is like saying we have some Gibbs sampler, so like maybe you're alternating through parameters, maybe it's these latent variables, right? And you're saying, okay, if we write the full joint posterior and then we break it down into the conditional so we can do Gibbs sampling, and we say, hey, this one, all the Gibbs samplers we're going to sample with whatever it is, maybe it's conjugate, or maybe you can do rejection sampling, or it doesn't really matter. But this one conditional that we want to sample from, we're actually not going to sample from the true conditional as defined by the full posterior. We're actually going to sample from some version which looks like that, but we're actually going to cut out the dependency on this particular data source. So you're actually like, you're sort of creating this posterior, sort of artificially creating this posterior, which is actually not the full posterior you originally defined. You're sort of saying, you're defining some sort of new posterior, which is by removing certain dependencies within these conditional statements. Now, it's actually not necessarily true that you end up with like a valid joint posterior, but you end up with better performance. So it's just a super interesting problem to me, where, hey, I have this like, I know how things work on a broad scale for sort of the full Bayesian model, but I also know I can solve problems by sort of hacking these things and sort of pinning certain variables here and tweaking things here and sort of breaking things, but breaking them in a way which actually produces better results and ultimately better decisions.
Yeah, that's fascinating. I love that. So basically, it's like, if I understood correctly, when you say cutting the posterior, it's like making sure we're only taking a subset of the full posterior that the model was actually defining?
Kind of, yeah, but only on one of the conditionals, so only on one of the variables. So you're saying, hey, when we learn about the speed, so normally it's saying, hey, if I'm updating, let's say, the variable for players' decision making, you have to condition on everything. It's the data, you give sample, you're also conditioning on the previous draws of all the other variables. But you're saying, then we're saying, okay, for speed, I actually only, when I update the speed latent variable, I only want to condition on the other variables, and the speed data, I don't want to condition on these other data. So you're sort of dropping the conditioning on these other variables and sort of just removing them from that conditional sampler. So kind of a really interesting case where you're sort of like just taking this thing that looks like a well-constructed posterior distribution and sort of just like hacking it in ways which is like kind of unprincipled, but like makes sense and leads to the performance that you want.
Yeah. Damn, that's really cool. So I'm guessing that means a lot of custom code, whether that's in Stan or PyMC or PyTensor, stuff like that, right? Yeah,
certainly, right. It's a lot of these things aren't necessarily handled well with Stan, right? Because Stan is great for, or any of these models, PyMC, whatever. They're great for, hey, let's build like a Bayesian model that does this, and this. But it's not great for when you're like, hey, we need to fix this edge case, we need to do this, and we need to sort of hack these things. So first up, to do those types of hacks, you have to like deeply understand the problem and deeply understand the models. That's sort of step one. But as you say, it oftentimes falls outside of these automatic inference engines. So you oftentimes have to do things custom, right? So, it actually reminds me a bit of like, I think a lot of times because of Stan and PyMC and others, like you oftentimes don't need to understand what's going on under the hood with HMC or any of these other algorithms, right? But I always thought it was important for people to understand, like at the very least, like what's going on when you're fitting sort of basic models. Like I'll give you one example here, which is when I taught spatial stats. It was a grad course. I would give people like a very simple multivariate normal where they're trying to like estimate the mean or the covariance or something, right? I'd say, okay, here's a whole bunch of data, and maybe P is 50 and N is 1,000. Hey, learn the mean and covariance, and that's like, oh, that's a trivial problem. It's conjugate, blah, 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 right? And then I say, okay, now I'm going to give them another data set, which is kind of the same thing, but P is now 1,000 and N is maybe 10,000. And all of a sudden, it's easy to pull in the data. The data is actually relatively small, but they go to fit the data and it just doesn't work. And they say, like, what's going on here? Why doesn't this work? It's a conjugate problem. Like, why doesn't it work? And they say, well, you're trying to invert a 1,000 by 1,000 covariate matrix, right? Like, maybe that's not a lot. Maybe it breaks down at 5,000, whatever it is. It's a pretty relatively low number on sort of a typical laptop where these things start to fail. And then it's okay, well, that doesn't work, so go fit it with stochastic gradient descent. And then they go do that, and they say, oh, actually, that works way better for these large data samples sizes. And I said, but what about for the small data? And they say, well, actually, then just use the sort of the conjugate one, right? So it's like realizing that, hey, there's different ways to solve the same problem, and you might use this sort of direct sort of analytical solution in some cases, and you might prefer to use SGD in another. And then I go back and say, actually, there's a piece of information I didn't actually tell you. There's actually a certain correlation structure in this data, and it turns out to be just an AR1. It's a time series.
Mm-hmm.
Oh, now you can just fit this thing with like, Kalman filter-esque kind of, message passing kind of ideas, but typically like Kalman filter-esque. So you can do things in sort of linear time in P, because P is sort of T now, like time, what you think of it, right? So, and then all of a sudden they go from an exact solution to something which actually is exact and very, very fast. So solving the same problem fundamentally, but understanding sort of there's different ways of actually doing the computation, right? And I think having those skills and sort of thinking holistically, not just about the modeling, but as well as the sort of fit, is really important. Like in sports where we're dealing with space all the time, you're sort of like, you're always having to discretize space in some way or another, right? Whether you like it or not, whether you sort of think about it as like, we're projecting onto some basis or something. Ultimately, you're discretizing. When you put it into the computer, it's discretizing it. So people oftentimes will say, "Oh, I like having a continuous model," but like, hold on, you're gonna have to sort of come up with some low basis approximation to it at some point. So might as well be sort of transparent that you're either having a sort of simple model that you can do like really accurate exact computation on, or a complicated model that you got to do approximate computation on. And sort of understanding those trade-offs, I think, is critical in anyone who's working on these problems.